So today I will through this Stirling's formula. And then I will work out some problems. Okay. So this is a plan for today's lecture. So let us recall whatever I wrote. So if Stirling's formula, there are 2-3 versions of it. The simplest one is this one, n factorial by n power n e power minus n square root 2 pi n goes to 1 as n goes to infinity. Okay. And more generally, so if you write, so gamma of t divided by t power t minus 1 e power minus t and square root of 2 pi t. Okay, this goes to 1 as t goes to plus infinity. And you can recover this by putting t equals n. When you put t equals n, you get n minus 1 factorial. Gamma n is n minus 1 factorial. But that's the discrepancy is compensated because you have here n power n minus 1, here you have n power n. So essentially it's the same. Okay. All right. Now, of course, here recall gamma t is integral 0 to infinity x power t minus 1 e power minus x dx. This is the gamma function. Okay. So we are going to prove this. It will use this Fourier inversion formula. So recall that if phi is the density function is equal to phi of xt is the density is the characteristic function of x with density f of x or fx of x, which we write as f of x. Then so you make one further hypothesis, and if f is differentiable, so in a neighborhood of x naught, then you can obtain a formula for fx naught is equal to, I think there's a 1 by 2 pi. Yeah, somewhere I think 1 by 2 pi integral minus infinity to plus infinity e power minus it x naught. Okay, and phi t integration is with respect to t, of course. Okay, so this is what we are going to use for a suitable distribution function. Okay, so what we do is the following. You start with the gamma distribution. Of course, you see that somehow if we are going to use these techniques that we have developed so far, or these concepts, then this, of course, it is related to the gamma distribution, right? So you better start with gamma distribution. So let y is equal to y have distribution. Let y have distribution gamma. Unfortunately, the parameter value is also going to be t. So there are two parameters for the gamma. The first one was called lambda, and the second one was called s, but in the place of s, we use t. Okay. And we let x is equal to y minus t, I suppose, by root t. And here, let us call this xt. Okay, the value xt depends on t. Okay, then what you need to do is find the density function of ft. So write ft for the density function fxt. Okay, the density function, and now you can compute what it is. Yeah, because we know. So you see, fy of t is simply divided by gamma of t, and here sorry, this I should not use t here, this should take little y. Okay, of course, this is gamma distribution with parameter 1 and this thing. So there will be lambda power something, lambda power s, that lambda became 1, so that factor is missing. And then y power t minus 1, yeah. So I write that. So here, the parameter value is t. See, this is a bit confusing. Remember what is y? It is this t, okay, which pops up here. So y power t minus 1, and then e power minus y. That's it. Okay. So this is the thing. Yeah. Okay. So it is this t which came up here. So we are going to see the problem here is that we are going to make a transformation there is a value t here. That t is same as the parameter value t. So you have to be very careful here, and it's easy to make a mistake. And therefore, what is the density function for xt? So f of, I just write here and then explain. You see, you must replace, yeah, you have to write. So you see, x is equal to y minus t by square root of t, or rewrite it as y is equal to square root of t times x plus t. And now you have to find also the differential. Dy is equal to square root of t dx. That's it, because we are treating t as a constant. So t is fixed for the time being. Later on, of course, we will allow t to go to infinity, but at the moment t is fixed and positive. Okay, so now what you do is you compute fx of t, which we write as f subscript t. This as a function of x. This is equal to, wherever you have y, you substitute for y. That's easy. Root of t x plus t whole power t minus 1 e power, sorry, some disturbance, I close the window, just only. So e power minus, in the place of y you write again the same thing, root of t x plus t, and then there is a square, so divided by gamma of t, and then coming from this dy is equal to square root of t dx, dropping the dx, we have square root of t. Okay, so we have this much. And now we try to find, so there are, yeah, what is it that we want to do? We want to compute ft at 0. So let me write that here. So it is for that value of x for which we will be applying the full this inversion formula. Okay, so you have this also called the Fourier inversion formula. So f x naught, that x naught is going to be 0. So I may write that for ft of 0, we are going to find it in two different ways. Okay, one way is directly by substitution because you know the density. So t power t minus 1. So, and also there is this root t in the numerator, so that becomes t power minus half. So e power minus t by gamma t. Okay, gamma of t. On the other hand, by Fourier inversion, yeah, by the inversion formula, but by the inversion formula, f0 of t subscript t. Before you apply, you have to make this appropriate noise, namely that you see f. So when can you apply? Only if the function is differentiable in a neighborhood of 0. And mind you, t is a constant in this function. So there's some square root of t, all those things are involved, but it's a t root. So this t is a constant in a neighborhood of 0. Well, I mean, x plus t whole power t minus 1 um, in a neighborhood of this one. So, okay. We have to, so you have this e power square root of t. This whole thing is a differentiable function of t in a neighborhood of t. There is a, see if t is close to 0, but this exponent is negative, but I suppose it doesn't really matter because this exponential square root of t is there, and so it should be a differentiable function in a neighborhood of 0. So in fact, you can just check that maybe if I take minus square root of t comma z, t comma infinity, in this neighborhood is going to be differentiable. So because you have minus square root of t coming here, which is perhaps why you have this. So this is just a routine verification. In other words, you just apply the formula for differentiation blindly, but notice that that formula is not going to be always valid. Definitely it will be valid for values of x in this range, and in particular, since t is positive, this is going to be differentiable at origin. Having said that, you can now apply the formula. I suppose there's a 1 by 2 pi in a formula, integral minus infinity to infinity And characteristic function. Okay, so now characteristic function of the distribution. So let me write that phi t. So e power minus I, uh, yeah. So we are going to write, because there's already a t. Usually we write something phi t dt, but we will use a variable u. So phi u 0. This is just 2. And then phi t of u du. Okay. So this is equal to 1 by 2 pi integral minus infinity infinity phi t of u du. Where now you can compute what phi is. Where, of course, I already written that phi t of u is equal to phi xt of u. So now you have to compute phi xt of u. But xt, is a very, bears a very simple relation with y. So it is y minus t by square root of t. So it's like a linear combination. 1 by square root of t times y minus square root of t. Correct? So therefore, just either apply the formula. So phi t of u is equal to, so okay, this constant will become e power minus I u square root of t, and then there is a scaling factor. So phi of uh, y u by square root of t, I suppose. I'll just write it and have translate that. Yeah. And y has a gamma distribution, and for which we already discussed the thing. So I just now write I u square root of t. And for the gamma distribution, I will write the formula in a minute, but I just write the value here. So it is 1 minus I u by square root of t whole power. So whole power minus s, but s is also t. So if you want, I can recall for you. I think for the gamma distribution, phi t. Okay, so if y is equal to gamma lambda s, so phi y t is equal to something like lambda minus I times t, I suppose, lambda, this whole power s. So here lambda equals 1 and s is equal to t, and the variable is just u by square root of t. I have written here. And when you do that, this is what you get. Okay. And now I go back. So what you need to do is, the idea is the following. You expand it. Okay. So this is going to be some function. Mind you, always remember that t is some number. Okay. Positive. And whatever expansion you write, you just write things formally. It is like 1 minus some 1 minus a whole power minus t. A may be a complex quantity, but it is valid in some neighborhood. So write this in a formal way. And yeah, we need to get it. See, ultimately we are going to allow t to go to infinity. Okay, so that is what you should remember. So this is e power minus iu t, iu square root of t times this, you write it. So exponential log e power log 1 minus I u by square root of t power minus t. So that becomes minus t here. Okay. So this quantity is e power log. So our exponent minus t, I have written it here. So this whole thing is e power minus. So I write that exponent a little more carefully in green color. I use square root of t minus t times log 1 minus iu by square root of t. This whole thing is in the exponent. I left out that u there. Okay. So now what you do is you look at only the exponent at the moment. I t, so minus I t u, I square root of t u minus t times. So you expand this log 1 minus something, all terms are going to be negative. Okay. And so there is already a minus, so I may as well put plus sign here. Okay. So now log, do you recall the formula? Log 1 minus a is equal to minus of a plus a, everything is minus. So a plus a square by 2 minus plus a cube by 3, blah, blah, blah. Okay. So I just do that in here. So I u square root of t, and then I square, that becomes minus u square by 2 t, and then plus, let's just write one more term, I u cube divided by so 3 t power 3 by 2, and so on. And you know, we are always going to keep track of the situation that we are only interested in allowing t to go to infinity, very large values of t. So this is equal to this I square root of t u, this plus I square root of it, they get cancelled. So I get minus u square by, so this t times t, that also goes away. I get this, and then some quantity which goes to 0 as, yeah, so big O of t power. So this t power 1 by 2 in the denominator, so t power minus half. Okay. And this goes to 0 as, yeah. So whatever, so this term will not bother you. And when you take, therefore, let us write now phi t of u. This is equal to e power minus u square by 2 times e power something, which is big O of t power minus half, and substitute that in the integral. So, sorry, so let me write one more step here so it's easy for you to follow. F0, this is what we are, ft0 is 1 by 2 pi, and then here you have e minus infinity infinity. I must write this. So when you write this, you get e power minus u square by 2. Well, and then, okay, let me just write it as O t power minus half. And here dt, du. Okay. Now, so in the limit, so here is some justification needed to take the limit inside, and the justification is provided by what is called this dominated convergence theorem. So as t goes to infinity, this O, well, t power 1 half minus 1 half goes to 0, and can write here. Sorry, I should. Therefore, and so now I take limit t goes to 0, t goes to plus infinity, ft of 0 is equal to 1 by 2 pi. Now take limit. First time you write limit minus infinity e power minus u square by 2 plus big O of t power 1 half minus 1 half du du. Okay, so now take this. So you see this, so long as the integrand irrespective of t, so here you see why is it that the dominant convergence theorem here is applicable, because irrespective of the value of t, mod phi t of u is always bounded by uh, yeah, some constant function. Okay, some constant that will do for us. So this is always bounded by 1. Yeah. Yeah, so rather I should say here, so I think this is probably not the right way to say this. Of course, this is true, but let's not. What we want here is that if I look at this quantity, and I look at particularly this part, that goes to the exponent here goes to 0, no? As t goes as so I want to say that this factor here is dominated by e power minus u square by 2. So that will do for me. And so I can take limit 1 by 2 pi. The limit can be taken inside, minus infinity, infinity, limit t goes to infinity. And e power whatever, minus u square by 2 plus o t power minus half du. And this becomes equal to 1 by 2 pi integral minus infinity, infinity e power minus u square by 2 du. But that's exactly equal to square root of 2 pi. Okay. And now put this there. So what goes to square root of 2 pi? Look at the thing that we already computed. So here, this quantity goes to square root of 2 pi as t goes to infinity. Okay. Therefore, limit t goes to plus infinity of, so I write f0 of t. I know already f0, the value of f0 of t, that was, it had gamma of t here, t power t minus half, and then e power minus t. Okay, this goes to square root of 2 pi. So therefore, you can just bring this in the denominator and write the numerator and flip it and whatever it is. So you get, this proves the result, proves the formula. Except that numerator has become denominator, denominator has become numerator. Is that clear? So that's all, there is nothing more. Yeah. So I'll work out some problems. We will take up the central limit theorem later, that's in the next lecture. So, exercises. Suppose that x takes values, x is integer value, integer valued. Okay. So in the one of the assignment problems also there was a bit of a vagueness in the language, but it is okay as written. So x is integer valued here does not necessarily mean that it takes its mass at each integer is positive. Okay. Sometimes the book uses this language. So x takes values 1, 0 plus minus 1 plus minus 2, blah, blah, blah. Sometimes it says x takes values in integers. So, when things are a little vague, it does not matter. They, so it just simply means in this context that x takes integer values. It may not be the case. That is, image of x is contained in integers. That is a meaning that one can attach to this. Yeah. So that it is in the same sense that I had I think maybe assignment problem number 1. X takes values in some a plus b times integers. So that doesn't mean that x takes every possible value of the form a plus bm for m any integer. It just simply means that image of x is contained in that set. Okay. All right. X takes values in this one. Show that. Okay. Yeah. Show that probability of x equals k is equal to 1 by 2 pi integral minus infinity to infinity e power minus itk, yeah, phi x of t dt. So, okay, so how do we do this? Now, what you can do is you can explicitly write the function this. By definition, this is expectation of e power it x, and x is discrete valued, so it will become sum. And here, in fact, it takes integer values. So here, therefore, you can write e power itm probability of. So you have to write the mass function, but I just explicitly write like this. Okay, you can write mass function if you want. Mass function, why confuses? Just write fxm. Okay, and m varies in integers. Okay, therefore, now you can integrate e power minus itk. That is, you start with this, right, and then try to simplify what you get. E power summation e power itm fxm, and m goes from minus infinity to plus infinity dt. This is from minus infinity to infinity. So it looks like a complicated mess, but it's not so. So integral, I just interchange it minus infinity to infinity integral e power minus it here m minus k fx of m and f. Okay, the integration is with respect to t, so I may as well pull it out. Okay. Oh, was there a 1 by 2 pi there? Maybe there was a 1 by 2 pi in the formula. Okay, it's here, right? Okay, just write this. Okay, so dt, this is from minus infinity infinity. Okay. I have 1 by 2 pi So let us integrate this. Okay, so this yeah, I suppose it has to be interpreted properly here. So if so, the thing is this e power it whatever it m minus k. When you do this integration, minus infinity infinity dt. This is e power it m minus k by oh, I suppose, sorry, the formula I wrote down incorrectly, and that is why I'm getting some nonsense, wondering what is happening. In the inversion formula, I have only here minus pi to plus pi. Sorry about that. Because minus pi to plus pi, minus pi to plus pi here also. Otherwise, I get something absurd. Okay, now you can compute this by directly doing this cos, integrating cos and sine. But notice that the value is going to be critically dependent on whether m minus k is 0 or not equal to 0. So your answer will depend on that. And in fact, this is going to be, so here, sorry, here minus pi to plus pi. Minus pi to plus pi. So here, so here I'm going to write here m minus k. Integration is respect to this. And you integrate it between minus pi and plus pi. But this is periodic of period 2 pi. So it will going to give you 0. But when it is 0, when it will give you 0 if m is not equal to k. So this formula is valid if m is not equal to k. Otherwise, this is just 1 and you get 2 pi if m equals k. And this is exactly what we wanted, because that means that in this sum, which is over m, okay, all terms except m equals k vanishes. And when m equals k, I get 2 pi here and 1 by 2 pi here. So all said, this means that, therefore, integral 1 by 2 pi minus pi to pi, whatever. So yeah, e power minus itk phi x of t dt is equal to f of k. And that is exactly probability that x equals k. Right? So I just show it to you together. So mind you have fx of k. So that's exactly the mass function. So I get this. Right. Written down some more problems. Yeah, I want to discuss one specific problem given in the book. Let me do that. I think I want to discuss the problem. Um, hmm. I've forgotten to note down the problem completely. Only scribbled something in my notes. So just 1 minute. Hmm. Okay, here is one problem which I want to discuss. Okay, so let me write the problem for you. So let yeah. I think I scribbled it somewhere. Yeah. Okay. So let's discuss this problem. So suppose that, so this is problem 2 for today. Xn has distribution function. So fn of x, instead of writing fx, f for subscript xn, I just write fn of x. This is equal to x minus sine 2n pi x divided by 2n pi 0 less than or equal to x less than or equal to 1. Okay, to take this, and you have to check that this is indeed um, a distribution function. So, okay, put put x equals 1. So first of all, you have to know that x is bigger than or equal to this always. That we will do that in a minute. But once you verify that, that's a simple verification. That this is always a greater than or equal to 0. And put x equals 1. What do you get? Here, sine is 2 pi periodic. So this becomes 0. Okay, so I get 1. So this is indeed a distribution function of some random variable, and that random variable is given. In fact, you can even find its density function. We will do that in a minute. But the problem is show that uh, limit n goes to infinity, fn of x, fn. Okay, so let me. Fn goes is uniformly distributed, is the uniform distribution 101. Okay, but the density functions fn of x, uh, yeah, does not converge. So the point is that you can have a situation where each fn is a perfectly nice distribution function. It even has a density. You can just differentiate it and compute it. This is a differentiable function because x is differentiable, sine x is differentiable, and so on and so forth. So it has a density function, and fn in the limit goes to the uniform distribution. Okay, but the densities do not behave properly. The density functions do not have convergence as n goes to infinity. So So let us compute. So note, so we find that fx of fn of x is equal to derivative. So d by dt, d by dx of fn of x. And here you just don't bother about other point, but only where it becomes, yeah, differentiable. And what is this? This is equal to 1 minus. So when you differentiate sin x, you get cos x. So cos 2 pi cos 2n pi x divided by, what is it? Sorry. So x cos 2n pi, 2n pi. So there is already a 2n pi and times 2n pi. So this and this cancels, and I get what? 1 minus cos 2n pi x. And this, of course, has no limit as n goes to infinity. Uh, so fn of x. So fix an x, okay, between 0 and 1. This has no limit, as n goes to infinity for 0 less than x less than 1. Okay, because this keeps fluctuating. All right. So there are some more problems I want to discuss. Let me just look at that. Yeah, use inversion theorem to show something. Okay, what is that? Minus infinity, infinity. Yeah. Okay, let me write that formula. So number 3, use inversion formula to show that, okay, integral minus infinity, infinity sine ax sine bx divided by x squares. Okay, let me write. Okay, fine. X square dx is equal to pi times minimum of a comma b. Okay, so I should have used sine at sine bt divided by t square sine dt. Okay, so that suggests that, somehow we have to realize this as the characteristic function of some variable, okay, some random variable. So we want to view this as, okay, some constant. You are related. We want to relate it to integral this formula, right? Minus infinity, infinity 1 by 2 pi. So this is for density function. Yeah, this is for a density function. Phi t, phi x of t, phi x of t dt. Okay, so there is a c power whatever. I'll write it and then I'll remove it, because see, if you recall, this is fx of 0 actually. So if you had x naught here, you will have e power I minus I t x naught. Okay, but that x naught is 0, so that factor becomes 1. So we just have this. So for some random variable, okay, it's not moving for some reason. Just 1 second. Yeah, for some random variable. Random variable. So what kind of random variable? So we need to search for a random variable. Need to search for a random variable which will have characteristic function sin at sin bt by t square times some constant, maybe, I don't know, but well, we'll have characteristic function, at least let us say related to this. Okay, related to this. How do we find that? You need to have some familiarity with these things. So let me just do this. Yeah, so notice that this is only a real valued function. So that already indicates that we should look for something symmetrical. Okay. So, well, I know this already, but you can try this following thing. So take uniform random variable on some interval. Actually, one should experiment it. Okay, minus 1 1 is the simplest thing. Okay, so try this. What do we get? Phi of t is equal to, write down the formula. So since it's concentrated only in this range, it will be minus 1 to 1. Yeah, e power I t x. Okay, and then here dx, fx dx, but f is uniform, so dx, but range is, this interval has length 2, so dx by 2, so I put that 1 by 2 here up front. So that's equal to 1 by 2. So this is even function, so we may just simplify this slightly. I think all this probably is not required, but 2 times. Let us do this. It takes time for me to do all these things. How much time I have? Okay, 1 by 2 e power my I t x divided by. So you can, if you don't want to do this, just write cos and sine. The sine part drops out, only cos tx part remains, and this is an even function, so I just get 2 times, so forget this. Is just integral 0 to 1 cos tx dx. That's equal to sine tx by t. Aha. Between 0 and 1. When you put 0, you get 0. When you put x equals 1, you get sine t by t. And so while this is close, but what we do is consider the uniform distribution on minus a. So take this time for the uniform distribution on minus a, we obtain sine at by t. sine a t by, I don't know, 80 or whatever. Well, I think it should be 80 here. Easy to find it, but no, 80 by t, not, there's no a there. Okay. So let x is equal to uniform on sine a t, on minus a, and y is equal to uniform distribution on minus bb. Then let z is equal to this where x and y are independent. Okay, so you take such distributions, x uniform on this, y uniform on this, and in such a manner that x and y are independent. Then let z is equal to x plus y. Okay, then what is the characteristic function of this? This is equal to sine a t times sine bt by t square. Aha, you got the integrand right. And now f of, actually, yeah, so okay, now I can integrate it. So what is the distribution? Okay, so I can now write the inversion formula. Inversion formula at 0. Okay, density function. See, these are both continuous distribution. This also has continuous distribution, and you can write down the distribution function for this one, and you need to check that this is indeed differentiable in the neighborhood of 0 and so on. And once you do that, you have this following formula: minus infinity, infinity, phi 1 by 2 pi. Let us not forget that. Okay, this is equal to sine at, sine bt divided by t square dt. Okay. So now if you can independently compute what this is, then it's a very simple matter to find what the answer is. Okay. What is fz at 0? This is equal to probability that, yeah, okay, sorry. You need to compute the density function. So you need to, okay. You can write more generally the density function for this by using convolution product. Fz of z is integral. Actually, I should write minus infinity, infinity. Write down the formula always. Fx of, okay, so x, and fy of z minus x. And here, the integration is with respect to x. Okay. But notice that, see, fx and fy, they are 0 outside of these intervals. Okay. So we want x to be within this interval. We want x to be, yeah, we want, okay, x to be, mod x to be less than or equal to a, and mod of z minus x is also to be z minus x, to be less than or equal to b. Okay. So then this is just one. Mind you, you are just integrating one. So when these are non-zero quantities, they are just each both equal to 1. So this condition kicks in only in the range of this integration. And I let you compute this. This turns out to be something like 2 times minimum of a comma b. Okay. Well, if yeah, see, this is why is it that you get 2 times? That's because this is going to be symmetrical. So it's going to be between minus c and plus c, and the value of c is minimum of a comma b. So that is the thing that I'm saying. So if x is, yeah, so suppose that x is exceeding this and x is positive. So we are assuming that a and b are positive. I forgot to say that. And yeah, I'm already writing minus a to a, right? So a is positive for me. Okay, so you can just a simple check that unless x and so this range of value, if it exceeds this minimum value, okay, I mean, isn't that clear? So for definiteness sake, suppose that a is less than or equal to b, then the minimum is a. But you see, if x exceeds that value, I'm going to get this term to be 0. Okay, so this is going to be equal to, and in that range between minus a and a, this is 1, this is also 1. This is always anyway 1 if it is non-zero at all. Okay, so without loss of generality, assume this, and now you will get a, once you assume this, then this integral will turn out to be equal to integral minus a to a just dx. That's equal to 2a. Okay, so use this and then try to complete the thing. Okay, I made one mistake here, I think, because it's not quite, yeah. See, what is the, I said this is 1, but it's not 1. This divided by a. This is divided by b. Okay, so I will have 1 by ab here outside this 1 by ab. And here 1 by, so I need to put the correct integral here. So this is so 1 by, yeah, this is 1 by 4 AB, because this has length, length is 2A and length is 2B here. So 2A times 2B, that is 1 by 4 AB. That's what is living outside times. So when you have this, this is what you get. And now you can simplify that this is turning out to be 2 times whatever. So please complete it. It's a very simple matter. So this is what you get. Yeah. Okay. So this is, I don't know if it is minimum or maximum. Maybe I made a small mistake. Maybe maximum. Maybe this is B, perhaps. This is B. Check this, please. It's quite possible I made a small mistake here. The limit could be B. I think it should be B here. It should be B. When A is less than or equal to B, it could so happen that because I'm subtracting something from here, right? So it is quite possible that z minus a is less than or equal to b. Okay, So this could be that I need to have B here and B here. Okay. And then this is 1 by this B, 2B by 4AB. That will get cancelled and I get 1 by 2A. And this, when you substitute, you get 2 times, there's a pi also coming. That's because there's a pi in the formula. So it will work out right. I checked that and it was okay. Yeah, so the main thing is to guess, how to guess that function. And in fact, I'm going to do 1 or 2 more problem which involves that type of consideration. So let me pull out that problem where you need to guess what is the random variable which has prescribed the characteristic function. So, okay. There are large number of problems. Some are difficult, some involve portion which we have not discussed in the class. So I selected a few problems which I want to discuss. Okay, so let me read out the problem. Let x1, x2, blah, 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 xn be independent variables with the characteristic function phi1, phi2, blah, 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 phi n. Describe random variables which have the following characteristic functions. Okay, so let me say this. So next problem, I don't know, 4 or 5. So let me put a dot here. So suppose that phi I is equal to phi of xi, x1, xn, independent random variables. So now find, yeah, find, so let phi is equal to phi1, okay, phi of t, just for clarity, phi1t, phi2t, blah, 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 phi and t. Find a random variable with characteristic function phi. So this is the first problem. Okay. Find x so that phi of t is equal to phi x of t. Okay. Well, in this case, it's really utterly easy. Take, let x is equal to, so just x1 plus blah, 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 xn. And remember that the density function or distribution function may be more complicated. In fact, we are not even told whether they are discrete or continuous random variables, but it doesn't matter because independence guarantees that phi of x of t is equal to, so by independence, phi x1t, phi xnt. Phi1t, phi and t in view of independence. Okay. So, so mod phi1 square, that's the next one. So the same problem, mod phi1 of x, sorry, phi1, let me say this. So this is our phi of t. I should have written that first. So in this case, how do you find? So note that. So phi of t is equal to phi t, phi1 of t times phi1 of t bar. Okay, but then let y is equal to minus of x2, minus of x2, or write minus of x1, it doesn't really matter. Okay, so let's say minus of x2, that's clear. Wait a second. So here x1, they are not identically distributed, so I want to write here y is equal to minus of x1, then phi1 of phi y of t is actually phi1t bar. Okay, you can just directly get it out of the definition of characteristic function. Okay, so this is something that we did perhaps last time also. Now take, let z is equal to x1 plus x2, where x1 and x2. So since x1, x2 is already used in the problem, I don't want to use x2, but write x1 prime, where x1 prime has the same distribution as as minus x1, and x1 prime is independent of x1. Independent of x1. Then phi of z of t is equal to phi of x1 of t times phi of x1 prime of t. Okay, and that's equal to mod phi 1 of t square. Okay, now I need to look at the book for the next thing. Yeah. Okay. D, yeah, this is 2 minus phi1t. Okay. Suppose 2 minus phi1t whole power minus 1. Okay. Yeah. This is a bit difficult to guess what it is. Okay. Yeah, so, but I want to discuss this all the same. So what you do is you write it like this. So this, I don't like this 2, I would rather like 1 here. So 1 minus phi1 of t by 2 whole power minus 1. So 2 power minus 1 comes out. And this, I rewrite it as a sum 1 by 2, formally expand it. Okay. Don't worry too much about this convergence business and so on. I guarantee that it converges. Let me tell you, I don't know how much background analysis you have, but anyway, you can apply Weierstrass mu test or Weierstrass m test to say that this is uniformly convergent. Whatever I'm going to write is going to make perfect sense. I'll tell you why in a minute after I write it. So 1 minus a power minus 1, that should remind you of geometric series, right? So this is phi1t power k divided by 2 power k, and k goes from 0 to infinity. Okay, why is it that this is valid? T, mind you, is a parameter. So, but the moment you put a value for t, this anyway, this is now going to be some number, maybe a complex number. But the thing is, what can you say about absolute value of phi1 of t? That's 1. So absolute value of phi1 of t by 2 is strictly less than 1. And that means that for any value of t. And that means that this series is convergent absolutely. Okay. So this is valid even as a function. And now once you have this, it is still not so easy to describe. I rewrite it like this. Phi1 of t whole power k divided by 2 power k plus 1. K equals 1 to n, 1 to infinity. Okay. Now, for each one of these, so for the numerator, phi1t power k, what is the thing, random variable that you can think of? You can also suppose that, so y1, blah, 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 yk, blah, 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 are independent, identically distributed random variables with the characteristic function uh, characteristic function phi1. Phi1 anyway identically distributed. I could have just said identically distributed as the random variable x1, but anyway it doesn't matter. Characteristic function x1, okay, with characteristic function phi1. Oh, sorry, I am out of time. So I will complete this problem in the next lecture. I really am out of time. I don't want to. So the thing is, let me just briefly say it because it takes only 1 minute to say it, having spent some 4 extra minutes. So what you do is, after you do this, then you consider y1 plus blah, blah, blah plus yk. Okay. Now this will have characteristic function phi1 power k, phi1t power k. All right. And now you are not quite done yet because you want this to be your characteristic function. So now you have to play a different game. You have to say, let z, this you call this z sub k. Now it is like, you keep tossing a coin several times and then, so you allow for a new variable n. N takes values 1, 2, 3, etc., k, etc., and consider the random variable which is z subscript n. So what does this mean? This is like, you just toss a coin until k turns, I mean, the head turns the first time. If it takes, and let n be the number of random number n that it requires for the head to turn, okay, in a fair coin. Then what happens? What is the distribution for this one? What is the random variable? This. So this given n equals k is exactly zk. All right. But probability of n equals k is 2 power k plus 1. 1 by 2 power k plus 1. And now you compute so then it's an exercise, simple exercise to compute the random variable, or rather the characteristic function of Zn. This is exactly whatever was given. Just do this. 2 minus whatever. P1t over minus 1. I should stop here. Sorry, I didn't realize I exceeded time. I stop here.
Thank you, sir.
You're welcome.